times the electric field, that's the electric field contribution, plus dq, the velocity of the charge crossed with the magnetic field. So if I express this in terms of the volume charge density, what's going to be? So this is going to be dF. So in terms of the charge density, I can write this as rho times d tau times the electric field plus rho times d tau times v cross v. Now, if this may not sense physically, but let's talk about force density. Just for the purpose of deriving Maxwell's tensor stress tensor. But physically, force density doesn't make sense, does it? So let's find the force per unit volume. Force per unit volume. I use symbol F, or we call it force density. So that's going to be dF by d tau, which is going to be the charge density rho times the electric field, plus rho v crossed with v. So what can you say about rho v? The charge density, volume, a certain volume charge moving current density. So this would give you F, the force density is going to be the charge density times the electric field plus the current density crossed with the magnetic field. Now, we recall two laws, the Gauss's law and Ampere's law, the modified Ampere's law. Gauss's law and Ampere's law. So according to Gauss's law, the divergence of the electric field must be equal to the charge density over epsilon naught, which means I can express the charge density rho as the divergence of the electric field times epsilon naught E and also the current density from Ampere's law, you can write it as the current of B minus epsilon naught mu naught time derivative of the electric field with respect to time is equals to mu naught times the current density. So I can solve for J here, and 1 over mu naught current of B minus epsilon naught time derivative of the electric field with this. So I can replace these two in the force density equation, and we find for rho, I have the divergence of the electric field times the electric field multiplied with epsilon naught, and for the current density, so that's going to be plus 1 over mu naught curl of B crossed with B and minus epsilon naught of dE by dt crossed with B. So when we talk about conservation of energy in electromagnetic field, we saw the Poynting vector, which is defined in terms of the cross product of the electric field and the magnetic field. So let's see if we can somehow express this in terms of the Poynting vector. So in order to do that, I must get something that involves E cross B and the time derivative, I think, on both. So if I take the time derivative of E cross B and applying the product rule, you can write this as dE by dt crossed with B minus E crossed with dE dB. Well, I have to take the plus if I keep the order. So E crossed with dB by dt. All right. So I'm interested in expressing this in terms of the Poynting vector. So if I solve for that, I will have dE by dt crossed with B is going to be d by dt of E crossed with B minus of E r crossed with dB by dt. It should be minus, shouldn't? Yeah, I'm just bringing this one. But how can I express, how can I relate the time length of the magnetic field with the electron? What law? Faraday's law. According to Faraday's law, the curl of the electric field is equals to minus of dB by dt. So basically then this so you can put this one in this form, dB by dt crossed with B is equals to d by dt of E crossed with B. So in place of minus dB by dt, then I can write the curl of B. All right, so that would give me E crossed with curl of E. All right. So now let's go back to the force density equation